Hello everybody, this is Dr. Eldik and today we'll talk about chapter 3 in semiconductors, and it is about the applications of the p-n junction or diode. The first application for the p-n junction is the rectifier, half-wave rectifier and full-wave rectifier. And simply that if you have a sine wave, you wanna rectify it, means that you just move the positive, for example, have the positive only, you clip the negative. This is a half-wave. Half-wave that you have the input like this, and the output will rectify it, which means that you remove or you clip the negative part. This can be done by a simple circuit like this. When Vn is positive here, this one here, then in this case, this diode is forward bias. Then when it is forward bias, then it is short circuit. It's almost short circuit, and you have a 0.7 volt. Then in this case, the output voltage across the resistor is Vn minus 0.7, which is 0.7 is small enough, very small with respect to Vn. Then we can say that this voltage is almost Vn. But ideally, this voltage here is Vn minus 0.7. But if it is negative, then in this case, this diode is open because it is reverse bias. Then you don't have any current in the resistor, and this means that you do not have any voltage. Then the voltage is 0. That's why you get the signal here. Then it is positive, where the amplitude here is almost the same like this one, minus 0.7. And when it is negative, when the input is negative, you don't have any voltage, 0. So this is explained here. You see, when it is positive, it is forward biased, so it is short circuit. And when it is negative, the diode is open circuit, and so on. Okay, so this is the same idea here. This is the same circuit, but this shows the exact value of the output voltage. So it is, as you see here, VL, the output voltage, is almost Vn, but less than 0.7. This is the difference here is the voltage across the diode. So it depends on what kind of diode you are using. What if we want to smooth this this wave here? So we have something like this, and then we have 0. We don't need it to be like this. We need it to be almost constant, for example. So how can we do that? We can do that by simply adding a capacitor. If we add a capacitor here, a capacitor parallel with the resistor, then what happens? When the diode is short circuit, when the diode is forward bias, short circuit, then you have a current. You'll have a current here. And this current will go through the resistor and the capacitor, and then it will charge the capacitor to its maximum, to the maximum which is Vn, or very close to Vn. Okay. Then when Vn is negative, then the diode is open. When the diode is open, then it will start discharging in the resistor. Then it will generate a current and it will produce a voltage across the resistor, which is the same voltage across, of course, the capacitor. Okay, so it is the same. The voltage will drop, but will not drop to 0 depending on the value of RC. So this is explained here. You have a capacitor and you have the same circuit, but you have a capacitor here. So look at the out voltage here. Then when it is the output voltage when it is on, when the diode is on, you have a voltage, okay, like this. Okay, when it is off, it is 0. Then on, then 0, and so on. But because of the capacitor, when it is on, you have a current, as I said, then it will charge the capacitor. Okay, it will charge the capacitor. When it starts dropping like this, then the capacitor will start discharge. Okay, and to a certain value, depending on the time constant, of course. Then after that, when it turn back to be positive like this, the capacitor is charging again. And then when the voltage starts dropping, the capacitor will discharge, and so on. So let us see how can we, what is the relation between this shape here or how this shape is changing with the time constant, which is tau, which is RC. So I did this the same circuit here using B2 Spice, and look at the input here. This is the input signal. And the output signal is this output signal here using B2 spice. And here was resistance is 1 kilo ohm, and the capacitance sometimes one time it was 1 microfarad, then I change it to 2, then I change it to 3, then I change it to 10. So of course in this case you are increasing the time constant because the time constant is RC. So let's see what happened. when when the capacitance is 1 microfarad, what happened? That you see the capacitor is discharging, then it will reach a minimum value of 2. Then the minimum value of the voltage is 2. Then the voltage is changing from what? From 2 to 4.3 here. The maximum is 4.3. Okay, 4.3 will not change because this is the maximum voltage. The maximum voltage is 5 volts. This is 5 volt minus 4.3. 5 volt minus 4.3. Minus 0.7, sorry, minus 0.7. 5 volt minus 0.7, which is 4.3 volt. When you double the capacitance, then in this case you double the time constant, and you can see now that the voltage is changing from what? From 2.8 to 4.3. So now the variation is decreased. When you change the capacitance to 3, then you see here that the minimum is 3.3 volts. Then the variation is from 3.3 to 4.3. Only 1 volt now difference. When you make it 10 microfarad, then you see here that the minimum is 4 volt. Then the variation is from 4 to 4.3. Okay, so you have almost constant voltage, average 4.15. So if you want to change this one, for example, R, make it 10K or 100K, you will get almost constant voltage across the capacitor or the output voltage. Next part is what we call it here, full wave rectifier. So instead of rectifying only the positive one, no, we need both of them, the positive and negative. We don't need to cancel half of the wave. We need to use both of them. So how we do that? Well, there are many ways to do that. Assume that you have a voltage or transformer like this, and then we have this voltage V2. And then Vn in this case is half of it because we have a ground in the middle here. So in this case, if Vn, if this point here is positive and this point is negative, if this point is positive and this point is negative, this will make D1 forward bias and D2 reverse bias. So this one will be open and this one will be short circuit. If this one is positive, okay. So now we will have a current here. The current will continue in this direction, and then we will move in the resistor, and also we'll charge the capacitor. We'll charge the capacitor. And if this one is positive and this one is negative, so this is actually the negative half cycle. This is the second one here. This one here, second half. Okay. If it is negative, in the half wave rectifier, it was not working. It was just clipped. But here, no, when it is when this one is positive and this one is negative, so we are talking about this part here. Okay, then D2 will be forward bias. So it will be short circuit, and D1 will be open circuit. So in this case, we will have a current through D2, and it will go through the resistor and charge the capacitor again. So now we have a voltage, and we charge the capacitor every half cycle. Every half cycle, not every cycle. Okay, so now if this is the input voltage Vn, which is half of V2, then the output will be like this. Will be like this. But of course, if we have, when you add a capacitor, then this output will not look like this. Will be smoothed. Will be something like this. As it will go up and then decrease, and then go up and decrease, and so on. Decrease and so on. This is the difference, of course, if we add a capacitor. But if we do not have a capacitor, this is how it look like. But ideally, this the green one, which is VL, is supposed to be the input minus 0.7 volt if this diode is silicon. This is one way to do the full wave rectifier. But the problem here is that the input voltage is half of V2. Half of V2, not the full V2. Then actually we divide the amplitude by 2. We can do that but without dividing the amplitude by 2. How can we do it? Using a bridge. So now assume that this is Vn here. So you see Vn, if this is V1 and this is V2, Vn equal V2. Okay. So now let us see if we have this one is positive and this one is negative. If this is positive, this is negative. What happened? Then in this case, we assume that we have a current like this. Then the current is moving like this, right? And we'll go until we reach this node. At this node, of course, this one is voltage is positive. Then in this case, this one will be forward bias. Then the current moving in this direction will not move in this direction because it's open circuit. Then in this case, this one will be a short circuit. Then the current is moving in this direction. And here will not go in this direction because it's also open circuit. Okay, so these two are open circuit now. So it will go through this diode D2 and then continue in the resistor and the capacitor. Okay, continue like this. And then we'll go back to close the circuit like this. Okay, of course, will not go in this direction because, as I said, this was open circuit and the voltage here is higher than the voltage here. Then it will go through this diode, which is D3, and then return back to the negative terminal. Okay, so now the voltage across the load is almost the same like the voltage across, or the input voltage here, the input voltage. But of course, practically it will be what? It will be the same voltage like this input voltage, but of course minus what? Minus the voltage across the diode. No, it will be the voltage across the two diodes, because in this path here we have two diodes. We have D2 and D3. In this case, if this voltage, for example, is Vn, then the load will be Vn minus what? Minus 1.7 minus 1.7. So it will be minus 1.4, minus 0.7 minus 0.7. So it will be minus 1.4 volt. Okay, 2.7 volts. Same if this one is negative and this one is positive. In this case, we will have the current from the positive terminal like this, and it will go this direction, until we reach this node. As this node, this one is open circuit because this is a reverse bias. Then we have the current will go through D4. This is forward bias. And this one is open circuit also because it will be reverse bias. Then in this case, the current will move through D4 and then continue like this, and then we'll go through the resistor. You see the same direction. Okay, then it will charge the capacitor again and go through RL again. Okay, and then return back to close the circuit like this. Okay, and then at this point it will not go in this direction because this was open circuit, as I said before. It will go through this one because this is a short circuit. It is in this direction. This is the forward bias, and then will not go through this one also because this is open. Then it will return back to the negative terminal. So in the positive half, and in the negative half, in both of them you have a voltage across the resistor, and in both of them you are charging the capacitor. If you do not have capacitor, then if this is the input signal, the output signal will be the same amplitude but minus 1.4 volt for silicon. So you see here we have the output signal look like this. And when we add a capacitor, then we can smooth this output. So it will look like this, and then after that, when the voltage tend to decrease, the capacitor will start discharge like this. Okay, as in like this, and so on. But you see the difference here between this one and half-wave rectifier. So if you try to compare them. Now assume that for this one here, the capacitor will discharge from here, from this point, to this point here. Okay, so this will be the minimum. But in the half-wave rectifier, the capacitor will start discharge from here and will go to the second one here, this one. Okay, so you see the difference between the minimum and the maximum is higher in the half-wave rectifier. So again, here, if you have a full-wave rectifier, the capacitor will start to charge from here, and then if we are going in a line, we'll go in this direction like this. So it will stop here for the full-wave rectifier. But in the half-wave rectifier, it will continue and stop here. And now we can see the difference between the two signals. That in half-wave and full-wave rectifier, you have a smoother curve. Okay. So this is a full-wave rectifier with B2 spice. So if this is the input signal, the output signal you see is almost constant here. It's almost constant with these values here. This is 100 ohm only, and this is a 2200 microfarad. This for the full wave rectifier. Okay, and see here, this is a voltage here. And as you see here, the voltage is not exactly here. If this the maximum is 24 volt, okay, which is 24, the voltage, the output voltage will be 24 minus between bracket 0.7 and 0.7. So it is 1.4. 1.4 from 2.24 will be 22.6 volt. So in this one, the average here will be around 22.6, 25 like this, 22.5 the average, but maximum will be 22.6 volt. So this will be the first application of the diode, that we convert AC to DC using either half-wave rectifier or full-wave rectifier. Something that we can notice here, okay, let's just talk about this one, and then after that we can continue. We can, with the bridge, if we add a ground here, and we add a ground here, then we add two capacitors and two resistors. So it's the same circuit. Instead of one resistor, we have two resistors, we divided by two, and two capacitors, okay, and then we add a ground here in the middle, and we add a ground here. What we'll have here, what we have here, we will have a positive and negative. You know, sometimes we have a dual voltage. You have an adapter that has dual voltage. It can give you, for example, positive 5 and negative 5 volt and ground. So if you want to create something like this from any AC signal, you take any AC signal from the transformer, then what you need to do is to put a ground in the middle like this, and you add two resistors and two capacitors, and in the middle you have a ground. So in this case, this will be positive voltage, and this one will be negative voltage, DC voltage. Before I go to the next one here, let's return back to the this circuit. Let's see this one here. Any one circuit like this. Okay. So actually, what happened here is that this circuit is acting as a peak detector also. So this is not only a half-wave rectifier, but also this peak detector, which means that it detects the peak here, the maximum, because it's almost curve fitting here. It's curve fitting. You connect this peak to this peak, this peak to this peak. Of course, if we have higher resistance and capacitance, then here this is the peak, close to the peak. So as if you are actually curve fitting for these peaks. Okay, so imagine that these peaks are different. So here are all the peaks are 5 volt, for example. But assume that this is 5, and this is 3, and this is 2, and this is 1, this is, and so on. So what happens that the output will follow the peak. So it will be peak detector. So imagine that we have, for example, signal like this. We have a signal like this. Then we add this circuit to it. What will happen? Will happen that the output will follow this peak. You see? So the output will go from this point, for example. The output will be here, and then we'll go to this point, this point, this point, and so on. Okay, so will be a peak detector. okay, will detect this peak. And this can be used in some application, like, for example, what to call it here, demodulation. Demodulation. This signal is called modulation in telecommunication. So if you have a modulated signal and you wanna restore the signal after that, we call it demodulation. Then in this case, the original signal was like this, just a simple signal like this. The demodulated signal is a high frequency signal, okay, like this one here, the one that we have here. But when we have a circuit like this, the output will be the we restore the original signal by detecting these peaks and then interpolating them. Okay. For example, this signal, if this is the input signal, the output will be simply, roughly, of course, the peak. You detect the peak and then interpolate the peaks. That's it. Okay. So this is one of the important application of the full wave rectifier, half wave rectifier, and full wave rectifier, of course. You can do also this one using a full wave rectifier. You can do the same.